it, please return it to a mailbox. So I'm going to pick it up 5 o'clock later today. And now I'm going to give you the information that going to be useful to you once you continue reading the book, because I'm probably at the end. So there is a HAP-TH paper. And so this HAP-TH paper is H124408. And so this is like a 60 or 80 page paper where all the problems in Polchinski book, or most of them, are solved. Okay. So if you have, if you continue reading and you still have a problem and you don't know how to do it, so this was done by Edric. Okay, so please consult that. Okay, so what I want to discuss today is kind of telling one of the fascinating stories that has been discovered in string theory and led to a much better understanding of non-perturbative effects in string theory. So that's an idea of T-duality. Okay, that's what we're going to talk. So it's T-duality. We talk about T-duality and toroidal compactification. Okay, so why do we need to talk about that? Okay, so remember that when we deal with a bosonic string, right, so for the bosonic string, the critical dimension is equal to 26. So that's how many scalars we need on the worldsheet of a string in order to get conformal invariance, right? And so if you continue reading more than 2, which is in the case of a superstring, the critical dimension is 10. Both of those numbers are larger than 4, and so what we need to do, in order, if we want to describe a real world, we want some of these dimensions to be compactified. Right? Some must be compactified. So what that means in reality, so that means that you have to think of them, that those directions, some of those directions, are actually periodically identified, and that's the simplest way to do a reduction from higher dimensions to lower. So in particular, what we can think that the scalars x sub I, that were free scalars on the worldsheet, are periodically identified. Ri, and so the index I from 4 up to 25. And so as long as, suppose any characteristic probe that we use if L, a characteristic size of the probe, so as long as L is much larger than any of these R sub I, so then effectively our probe will live in 4 dimensions, right? So the probe dynamics in 4 dimensions, okay? And so that's kind of the logic behind obtaining some semi-realistic or realistic scenario of our universe coming from string theory. So identification of some of the coordinates on a circle is known as toroidal compactification. So what we're going to do, we're now going to study toroidal compactification in field theory. We're going to see what are the consequences. And then we're going to study toroidal compactification in string theory. And then we study toroidal compactifications in string theory, and we see drastic differences. Okay? So let's start with the field theory first. Okay? And so what I'm going to describe now is the idea due to Kaluza and Klein. Right? So we can talk about time rectification. Okay. So let's look at general relativity in d dimensions. Okay? So I have a metric with given g and dsm. And so what I'm going to do, I'm going to choose to write this metric in slightly different way. So I'm going to isolate this guy with d dimensions. So I'm going to separate, break the metric into a d-1 dimensional piece and the remaining dimension. Okay, so I'm going to write it down as d mu dx mu dx mu. So this is d-dimensional. And so that will be little d plus 1. And then I'm isolating one extra coordinate. So I'm just going to write down the metric in this form as c plus mu dx squared. Okay. And so notice that at this stage I have done nothing. Okay. So this is just a simple way of rewriting a d-dimensional metric. So this guy is d by d matrix. So what I can do, I can write it as a d mu nu, right? Well, it's not going to be exactly this, you have to deal with it. But basically what I'm doing, I'm breaking it into d block, right? Then there is a component gdd, and then I have a nu here and a nu here, because the metric must be symmetric, right? So this is the most general decomposition. Most general decomposition. So you can see why I put the tilde here, right? The reason is because once you open up this, then there is a contribution dx nu coming from a mu, right? So it will be. But I have done nothing. I didn't remove any degrees of freedom or anything at this stage. Okay? So what I'm going to do now, I'm going to assume that this remaining coordinate is periodically identified. So we're going to, instead of going into complications of trying to compactify lots of coordinates at a time, we're going to look at the case when only one of them, the last one, is compactified. So I'm just going to do periodical identification. So xd goes to xd plus 2 pi r. So r is the radius of the d-dimensional circle. So the whole idea on Kaluza-Klein compactification, which kind of goes to this notion that the size of the probe is too big to actually move in this compact directions. So we're going to assume that everything that is left, so in particular this part of the metric and this vector field a mu, as well as a component gdd, does not depend on this compactified coordinate, right? So, so we're going to assume the assumption that del g mu nu over del xt equals to del mu xt 0, right? So nothing depends on this xt coordinate. And so what we're gonna ask now, what's the resulting theory look like? Okay. So before we know what the theory was, right? So in d what we had a standard Einstein-Hilbert. I don't have anything else, just an Einstein-Hilbert showing D dimension. And what we want to know that given this, after we make a reduction on the circle, what the resulting low energy effective action is. So before we proceed, right? So let's think what kind of symmetries we have, right? Well, so before, so in D dimensions, we have d-dimensional diffeomorphisms. Okay, and so now once we said that nothing depends on the xd coordinate, so the unbroken group of symmetries will be a little bit less. So in particular, what we can do in little d, which is capital D minus 1, we have a diffeomorphic group in D dimensions. Right. So what I mean by this, that any of these coordinates x mu, right? So we didn't put any constraints on them. So what I can do, I can still do a change of coordinates there. So x mu goes to x mu prime, which is a function of all coordinates. But then there is one extra symmetry that I can do, and so that relates to this xd coordinate. So I cannot. So xd is a circle, right? And because it's a circle, it doesn't have an origin. So what I can do, I can shift the xd coordinate when I make a little d-dimensional diffeomorphism. So in other words, xd goes to xd prime, which is xd plus some arbitrary function lambda of x mu. Okay, so that's still an allowed transformation, which is a part of the larger diffeomorphic groups in capital D dimension, and it still leaves other answers. Right? Is that clear? Yes, because see what happens is that anything that I do doesn't depend on xd. Right?
Yes, but if we transform xd,
well, there will be a Jacobian transformation, but it's still, it's just the Jacobian is 1 because I'm not mixing x mu with xd, right? So if this guy will depend on xd as well, then there will be a non-trivial Jacobian transformation, and so those conditions will be violated. But this is not. Just pure shape is not. So the easiest way to think of this is that now, so this, how does this condition look like, right? So now I will have gx mu and exd prime, which I can write down g mu over dxd dx d dx d prime. So that clearly is just 1. Okay. And so you can see that all these conditions that we impose, that nothing depends on the circle, right? So they still remain after this transformation.
I have a question. Why will we need to preserve the
No, we don't. I'm just saying that what we're going to do, we're going to look at the consequences, and we're just going to explore what will happen. If we compactify, reduce a theory, right? Go from high dimensions to lower. And the logic behind this is really the logic here. I think I just didn't want to say it because I thought it's you guys should have seen this argument, but I'm happy to repeat. So suppose I have so this is the simplest way of thinking about compactification, right? If I have a sheet of paper, right? So if I put an end on that sheet of paper, it can go anywhere around, right? Now, if I put and also if I put a small end here on a piece of chalk, so notice that a chalk is a sheet of paper when I reduce one of the dimensions of the circle, right? So if I put an end here, it can still go anywhere. It will still see it as a two-dimensional circle. And now if I put a koala bear here, what would happen? Koala bear can only think about this piece of chalk as just moving up and down, right? So it will not, it will not even understand that it can, go around it. So in other words, if we have a probe, if we have an object that whose size is much bigger than the size of compact dimensions, then effectively it will not, that object will not move in the compact direction. The mathematical way of stating this is precisely what I stated here. That the metric decomposes, I did the most general decomposition of the metric, and then I said that, look, the metric depends on some object, G mu, GDD, and the vector field. And so the fact that my koala bear doesn't see this circle implies that all these objects are independent of this coordinate. Now, once I make this physical statement, I'm asking the question, once I do that, what is the remaining redundancies? What is the remaining symmetries in the problem? And so the remaining symmetries is that I cannot touch XD coordinate, I cannot mix XD. But there are two types of transformations that I can do. I can make the whole transformations as long as they do not touch XD coordinate, and then I can shift the remaining coordinate. So now, so is it?
Maybe
Yeah.
Sure. More general. So, can we derive such conditions if we say we have general metric and we have the matter and we write down the Einstein?
Yeah, we'll talk about meta. So you can.
I mean, if we have like we don't have such conditions, but we have some kind of special matter which leads us to this condition.
That is not going to be okay. So it's not going to be imposed on you by equations of motion in any way. Again, going back to my problem with a koala bear and an ant, where the chalk itself, the surface, doesn't care who falls on it. What is important is what the size of the probe. So what that should immediately tell you that, I cannot get conditions of this type, that something does not depend on what is coming up naturally from solving some equations of motion. Those are the properties of the observable, physical observable. So what we are asking, you have to think of it this way. So there is a theory, and the theory has to be interpreted by an observer. That observer can be either M, or it can be a koala bear. So if the observer is the N, then what the observer will see, if the observer will start constructing the theory, he will see this. He will say, okay, everything that I observe is described by this effective action. It's a capital D-dimensional theory, and it has this Einstein field. Now, koala bear doesn't see the circle. He just doesn't see it. He just has to grab it, and so he just grabbed it and it moves. Never even understands. In principle, maybe he can move there, but he just doesn't understand and doesn't see that he can move. He wants to interpret. How will he construct the theory? The theory microscopically is the same. The theory is given by microscopically by this action. But what we are now trying to do, we're trying to construct an effective description. How would the person interpret the measurement result if he is making the assumptions that he cannot move them? And sometimes it's not an assumption, right? So again, if the object size is too big, then he physically cannot move in that direction. You will see in a second why. You would say, why a koala bear cannot go around slowly? The problem is that thing will be quantized. Right? Once we go to quantum mechanics, because there is no continuous momentum. The notion of going slowly doesn't make sense. Eventually, we're going to be doing quantum mechanics.
So these conditions are becoming
No,
case,
again,
so-
that's right. So as long as, of course, so those conditions are better enforced, because there is the point is that when we write this thing, we concentrate on wide degrees of freedom, right? So in this case, a massless d-dimensional gravity. And so what will happen once we compactify direction and quantize, that's what we're going to do in a little bit, is that there will be a massive, there is no notion of moving, with infinitely small energy. You either have a zero energy around the circle, or you have a quantized energy. Okay. I'll go through that in some detail. And so that's why, by definition, we are looking at the low energy states, low energy excitations, and so the separation, as you said, will be more, from this perspective, more precise. All right, guys, so let me go back where I was. And so now we understand that there will be a part of diffeomorphism, high-dimensional diffeomorphism, which will be left unbroken. And we can ask the question, so how does our field transform under this remaining transformation? Well, so G mu transforms as a rank 2 tensor. So exactly the way how the metric would transform. Right? So GDD component, GDD is a scalar. Okay? So it doesn't transform. So in other words, so the only thing that will happen is exactly as it happens with the scalar. So GDD as a function of x mu will go to GDD prime as a function of x mu prime, which is identical to GDD x mu. So that's the transformation for the scalar. And then finally, we have this vector field, E mu. And so this guy will transform in a very interesting way. So it will transform into A prime mu, which is going to be equal to A mu minus del mu of lambda. Right, remember that lambda was defining for us an additional type of diffeomorphism. Now, if you recall your gauge theory class, then what we have here is this vector A mu, which is one of the components of the metric here, actually transforms under diffeomorphism, high-dimensional diffeomorphism, as a gauge transformation. Right? So this is gauge. So in other words, what we are finding that when we do this simple reduction on a circle, what will happen is that some part of the components of the higher dimensional metric will start behaving as a gauge field. And it's not just a vector field, I emphasize it's going to be a gauge field. And it will come with its own gauge transformations, and those gauge transformations are inherited from the higher dimensional diffeomorphism. So, so we understood the symmetries. Now let's go back and let's try to see what will happen. So what we're going to do, let's look at the massless scalar field. Okay, so we're going to look okay. And so what I'm going to do, I'm going to assume for now that this component of the metric GDD equals to 1. What the scalar can do, right? So the scalar field can move along d dimensions with coordinates x mu. And then what it can do, it can also it can also, its wave function can also depend on a compact direction. So I have a scalar field, so it depends on x mu, and so the wave function, so the scalar is that it's a massless scalar, so it satisfies, this wave function satisfies simple equation box of phi in d dimensions equal to 0, which is the same as nabla m x to phi 0, which is the same 1 over square root minus gd L m that's what this motion. So what I can do, well, I think let's go a little bit faster, but there is a way of understanding it by simply trying to solve this equation, just trying to solve this equation on the d-dimensional metric. But something that we already know, and I'm going to take this shortcut, is that momentum of the scalar field, momentum of phi along its d direction is quantized. Okay? And so it's going to be quantized as momentum equals m divided by r. And so when I'm looking for solutions to this wave function, I can decompose the wave function for the scalar field in terms of, I can do a Fourier decomposition. So this is actually the way how you can think what you are doing. You are solving this equation by doing a Fourier decomposition of phi along this compact direction. It's going to be I n of x mu e to the I n x d over r. Right? So I just did a Fourier decomposition if you just applied instrumentation, for example. But in reality, what I have, I wrote down what is going to be a dependence of a wave function of a scalar field in this compact direction. And it simply takes the form e to the I momentum times coordinate. Right? So this is just e to the I times this. Okay? So our scalar field is a free massless scalar field. And the circle is just a simple circle. Okay, so there is a way to understand, there is yet another way to understand this dependence.
Is it x mu in
Yes.
before the exponent?
No.
Or xm?
No, it's xd. That's a compact direction. Here is xm. So what is happening is that, okay, so there are two ways to think about this, right? So one way is you have that equation, you just have to solve this equation. So that equation has a circle. So what I can do, I can find the normal modes on the circle, right? So those will be these exponentials e to the I x xd over r. And I'm just going to decompose my function phi in terms, just do a Fourier mode decomposition along this compact direction. That's all I did from the mathematical perspective. From the physical perspective, what I am saying is that the wave function of my scalar is a superposition of wave functions, right, of different states. So each state has an index n. And so that index n implies that there is a particular dependence of a wave function, right? It's exactly, if I would ask you, write down the wave function of a field, right, along the compact direction. It will be of the form e to the I PD times xd, and PD will be quantized. It will be, PD is going to be equal that's if you wish a physical way. Right? But mathematically, you can think of all I'm doing, I'm solving this equation, and I'm just going to write down. So this is the exponentials make a complete set of functions. Right? On the circle. So I just decomposed it. And what I can do, I can just plug it back in. You will see what will happen. Okay? The only thing that, one other thing that I want to point out, which is kind of lies in the idea of Fourier decomposition. Again, so this pi is must be a single value function, right? So this pi, well, I put x and so if I shift xd by 2 pi r, the wave function must go back, right? So that's a physical way. So this is a single validness condition of the wave function. And mathematically, that simply the condition that determines me the appropriate eigenfunctions. Okay? All right, guys. So we have the scalar field, and by the way, here I'm not making any assumption. Am I a koala bear or am I an ant? It's just the most general expansion, right? So, most general expansion. No approximations have been made. So here I did not yet make an approximation. Does it depend on xd or not? Right. So you can see explicitly that this scalar field, it depends on all four. So now what I'm going to do, I'm going to take this ansatz and I'm going to plug it in the equation of motion. And so I want to know how this equation will look like after I make this substitution. Okay? And so that will lead to number mu of phi. Right? So this operator acts in d dimensions. And then notice that in this wave equation, the derivatives go over all coordinates. So then there will be a derivative with respect to xz. And so that will bring in this extra term. N squared over r squared by phi sub n. These guys will be on x. Okay? So I'm doing this decomposition for each mode. Okay? So I'm just going to substitute each term in this sum.
And again, it's x, f, and x mu.
So the same n that is in here, the same n is here, right? So those guys depend on x mu now.
X mu. And there, x m.
So right. So there, the whole dependence, right? Okay. So how do I do? So let me look at this. So let me show you. So this del m square root of minus gd gmn, right? Del m of phi. So first of all, it's a linear equation, so I can look.
It's okay. Yeah.
You see where it will come from?
Yes. Simply, I don't understand why there are. So there is f and x m or x mu.
Here is x mu.
X mu. Okay.
So this depends on x mu.
Okay.
So I explicitly.
I thought you said it x first.
So now you can see that a massless scalar in d dimensions looks like a massive scalar. In actually an infinite number of massive scalars in little d dimensions. Right? So one massless scalar in d dimensions is equivalent to a Kaluza-Klein tower, an infinite set of massive scalars, infinite set of massive scalars So those masses, mn squared, are just related to this Kaluza-Klein momentum. Okay. Now, remember that in the string theory, the situation is kind of similar, right? So there were massless states and there were massive states. And so what we did in string theory, we derived equation of motion, right? And we derived effective action, equation of motion, and effective action for massless fields, right? For massless fields. And the reason we did that, we said, look, there are massless fields, and the next massive field, they come up massive string modes. They have a scale 1 over L string, which is 1 over alpha prime, so 1.5, right? And so if we make an assumption that alpha prime is small, the size of the string is small, then this mass is very large. So as long as we do any physical process whose energy is much less than the mass than the string scale, then we can never observe them. So the idea is we should apply this idea here if we try to come up with the low energy effective action. So if we concentrate only on low lying modes. So remember, if we look here, what is happening, so I'm plotting the spectrum of this leaf, so m squared, right? So there is a state here, so this is n equals 0, then there is a state here, n equals 1, so this guy is 1 over r, this is 2 over r, n over 2, and so on, right? So again, what we see is that there is a mass gap. There is a mass gap in the spectrum, and so if this mass gap is huge, or for example, if I'm going to make an assumption that the radius of compactification is roughly the string size, then by the same logic that here I neglected massive modes, what I have to do here, I have to restrict any physical experiment that I'm going to do with this massless state only. Okay? The point is that it requires at least the energy 1 over r for me to excite this next mode. Something similar to what we have in string theory. It requires a lot of energy to excite string. But now, once you understand that, so light mode is only n equals 0. Right? So it's actually a massless mode. And so now you actually see what I was referring to before, that in this case, the wave function, right, so phi 0 of xm is going to be equal to phi 0 of x mu, right? And then I have e to the I 0 over r times xt. So you can see that precisely for the 0 mode, precisely for the light state, the dependence on the compact direction drops out. So this is a way, this is maybe a more precise way to think about Kaluza-Klein reduction. So if you do Kaluza-Klein reduction, again, the reduction itself doesn't care. Everything will depend on this compact coordinate. But then you start asking the question, if I look only at physical processes, the process is so that my energy is less than 1 over radius, right? Then that's a physical way of saying that quantum mechanically you will never be able to see that you actually have a circle. You will simply think that there is nothing else.
How about if we have a photon in our capital D dimensions, so in our reduced dimensions we still
We'll talk about what will happen. So for now, notice that for now, what I'm doing, I'm talking only about, actually, I I even stopped talking about Einstein-Hilbert. For now, we talk about the scalar, simple scalar field. And what I showed that the idea by saying scalar field does not, I'm just giving you a physical meaning to the questions. What does it mean? Your field in capital D dimension does not depend on little d dimension. And the precise meaning that simply means that there is a whole infinite number of states. Like if you think from the lower dimensional perspective. By the way, whether you think in terms of this or you think about, this is what this equivalent sign means. There are two ways you can think of it. You can think that you have a single massless scalar in capital D dimensions, or you have infinitely many scalars in little d dimensions. Those things are equivalent. It doesn't matter how you think of it. The point becomes that now, if you are doing experiment with low energy, then all this infinite set get reduced just to the lowest mode. And that lowest
massive scalars and do we have always massive scalars, or just we sometimes when we are in low energy we have massive?
Okay, so your question is, are there going to always be a zero mode? No, the answer is not. It will not be always. For example, if I would have a fermion, then there is a way how I quantize it that there are no massless modes. So it's not always given. In this simple example that we do have a massless mode. But the important thing I want to emphasize with this example, so if this is a zero mode, then it doesn't depend on compact order, right? So remember, we started with kind of heuristic idea that we want to have a large observer and he doesn't see this. And I'm saying that actually corresponds only in the case when the observer has a zero energy in this compact direction. And it's a well-defined notion because the energy is quantized, right? So there is a mass gap here.
So this statement should be a set of massive and one massive.
There is infinite
set of massive and massless.
One massless gap. Okay. And the point is that if the mass gap is huge, we can just restrict our attention from massless. Right, guys? So now let me go into one more thing, one more comment that is useful. So what's the physical meaning of this M? Right, so you could say, well, it doesn't have real physical meaning, it's just a Fourier mode decomposition, or if you wish, it's an index with a mass, but in fact, there is a well-defined physical meaning for this M. Okay, so let's talk about that. So remember that in one of the transformations that we had in our one of the symmetries that we had in our series was a symmetry in which xd was going to xd plus lambda, and this lambda depended on x mu. And so we understand what this transformation corresponds to. That's a transformation that corresponds to a gauge transformation, right? So because our vector field a mu was going to a mu times minus w lambda. Now, if I look for the nth mode, right? So now, say I choose a particular scalar here, and I write down the wave function for this scalar. So it takes the following form. It's f sub n of x mu e to the I n over r x e. And I want to ask, if I do this transformation, what will happen? What will happen with my wave function? Okay, so this is a wave function. Of nth mode, right? And so, well, it's clear what will happen, right? So the wave function will go back to itself. And then it will develop a phase, right? So the phase will be I, and then I have n over r, Now, if you go back to your quantum mechanics class, then you recall that if I have a wave function for some state, right? And so if that state carries a charge Q is a charge, you can think of this as being electromagnetic charge. Then if I do a gauge transformation, the wave function will pick up the phase, which is the IQ times gauge parameter. So what we are discovering right now, that this n, or more precisely a momentum in the Kaluza climb direction, serves as a charge under this U1 gauge field, right? So AU was a U1 gauge field. And so what we discovered with you that PD of n is the same as a Kaluza climb charge. Right? So in particular, all these massive Kaluza climb modes, you can think of them as being charged states. So those are like states that there is 1 unit of electric charge, 2 units, and so on. So in this particular example, the state with n equals 0, massless mode, the one that we end up actually focusing on our physical experiment, is neutral. But this is not always the case. So the reason is that here we look at a very, very simple situation where we just have a bunch of circles. And so in cases like this, the massless mode will always be neutral under the gauge field. There will be gauge field, but the massless mode will be neutral as in here. In more complicated cases, what could happen is that these n equals 0 scalars that you get are actually charged scalars. So in fact, when people look at the realistic scenarios of the worlds that come from string theory compactification, you actually need to have massless charged scalars. Right? So all the quarks that we see, all the electron, for example, it's a charged scalar field. And so it better come from a string theory as a light in this the limit that we're talking about massless state, but it must be charged. So it means that in order to get a realistic world with electrons and quarks that carry charges, you actually have to do something better than just toroidal compactification. A simple toroidal compactification of the particle. Okay, so is that clear? All right, guys, very good. So now we can actually go back to our problem, and we're going to write down. So now we understand what it means. What this condition means, it means that once we reduce on a circle, there will be massless modes and there will be infinitely many massive modes. And so what we're going to do, we're going to try to write down the effective action in d dimensions, and this effective action includes only massless modes. Okay, the logic being is that the same logic how we derive effective action for bosonic gravity, right? So we just looked at massless mode. All right, guys. So any questions?
So this SD is not realistic.
It is as realistic as the effective action we were writing from string theory. It's an action where you are making an assumption that you are a low energy person.
No, I mean
you are not testing Planck scale physics.
It doesn't have a massive.
The same way. Well, okay. So right. So
I did just
you should not be. So what could happen is that you start with a massless mode, but unless it's a gauge field, typically there will be quantum corrections that will generate small mass. So in a string theory, when we derive the model of the world, we derive a model of the world where all the states are massive. The first approximation. The reason is that being massive in string theory implies actually the massive state means that it's a Planck state. 10 to the 16, 2 times 10 to the 16 G, way above anything. So from the perspective of this energy scale, all the states are massive. So of course we cannot look at the realistic scenarios, and we cannot. Then it will be just a field theory calculation.
Okay, simply just as a classical.
If you wish, you can think of this as a classical level and a simple compactification. So it produces, first of all, neutral states, and second, it produces exactly massless states. So that's at the classical level. So in principle, scalars will develop mass. The gauge field cannot develop mass because it's no longer going to be a gauge field. A vector field must be massless, and it is protected against receiving massive corrections, unless, well, in principle, there could be a Higgs mechanism, but that's spontaneous symmetry break. But it cannot happen in the simple compactification because there are no charges. So I'm pouring so much information on you, but it's good. This is, I want you to understand the real physics.
So
the
we
real
will derive in our reaction if we consider not simple compactification, right?
There will be, right, and so there is a lot of work in string theory is actually come on finding the effective action. That's under the notion of effective action. So you look at the light modes and you write down the field series that describes it.
So
you go from the full string theory. See, nobody can solve string theory with infinitely many fields. Right? What you have to do, you have to be realistic, and you have to find a sector of the theory that, first of all, not only it's realistic for you to solve, but it's also realistic to reality. Right? And so that's why the whole point, if you wish, finding the right compactification is exactly the same problem as finding the right effective action. Put it the other way around. It's a kind of backwards. We know what this is. Now what you have to do is you know exactly what this is. Stuff that we know to think how the extra, in this case, 6 dimensions, right? We have to do superstring, has to be compactified so that we produce the right spectrum of massless modes with the right charges. So that's what people who do string phenomenology do. But you are absolutely right. If you do a string theory, much like in the case of a scalar, that was an approximation when I said that I'm just going to look at the massless mode. What I can do, I can ask the question, what is the correction if I include this mode? Okay. Suppose that instead of having the energy of my accelerator here, I have it slightly above. So what will be the effect on my action once I include one additional massive mode? So this is exactly the type of questions you want to ask when you look for new physics. Because that suppose you found a string theory which gives you the standard model, but from the research perspective, from the perspective of confirming the string theory, you haven't done anything. Right? What you did, you kind of showed how that thing is in string theory. If you want to confirm the string theory, once you found this, you have to say okay, so this is an approximation when I neglected the massive state. Now let me include the first couple massive states and see what are the corrections to this action is. Once you compute this correction, you have to ask the question, what are the observable consequences? How does my cross-sections depend on that? Are there any other physical effects that I will see? And if you're, that's the way, so when people are saying the string theory is not falsifiable, I kind of disagree with that precisely for this reason. There could be lots of models, right? So there is, there are different compactifications of string theory. They produce a different one. But once you pick up the one that describes your world, the string theory makes a very specific prediction on high energies, or what are the corrections to it? What is the physics beyond the standard model?
Yeah, it's clear. So my question is, if we take another compactification, so in this compactification, if we elaborate this, we just get photons and gravitons, not fermions or other stuff. So, and if you take another compactification,
in a bosonic string, you will not get it, but you will get only states of integer spin. You will get higher states of higher spin.
And we will get photons as well. So if
in a superstring, yes.
Yes, okay.
And what I want to discuss today is that you have to be very concerned. And this is something that, how many of you guys know non-abelian gauge signal? So you know a little bit. So what you have to be concerned is that, well, it's kind of problematic, right? So what you are showing that there is this U1 towards the client gauge signal, but it's a abelian gauge signal. So it's so happened that it's always in a field theory. What is always happening is that you're going to get a abelian gauge group, which is not what we see in our real world. Right? So the standard model is based on non-abelian gauge signal. If we want to describe nuclear physics, we need non-abelian gauge signal. And so that's something that I'm planning to explain later today. How does non-abelian gauge symmetry show up in string theory? Which means that string theory has the right ingredient to describe the theory we live in. Now, if you ask me, did we succeed in this? Okay, did we actually find the first step before going ahead and making prediction what comes next? Did we get this zeros order approximation? And I would say no. I mean, there are models which come close, but not quite. So there are still work needs to be done. All right, guys. So let's go back. To deriving effective action, right? So remember that the metric of this form, G mu dx nu plus GDD dxt plus A mu dx nu squared. And so our effective action in D dimensions, the action in D dimensions was 1 over 2. So what I'm writing here, so this is just the Newton constant, 16.5 G Newton in D dimensions. Sometimes people write it as a gravitational coupling, right? And so here I have EXT minus GD scalar in D dimensions. So there are two ways how you, what we want to do. We want to derive an action for these three objects, right? And there are three ways. There is one honest way how you do it, where you can actually follow pretty much doing the same what we did with the scalar field. So let me put again the scalar field back into play. So for the scalar field, what we started with this action, like GD, and then I had del m5, right, minus 1/2, right? So that's an effective action for the massless scalar field in D dimensions. And so how can I go into little D dimension, right? So one way to do it is to write down the equation of motion, what we did, and then we saw that there are infinitely many states. But for the massless mode, the equation of motion is just nabla mu not let mu of phi equals to 0 for the massless mode. So if I am going to guess now, what is the effective action that leads to this equation of motion? The answer is so I know that massless mode described by this equation. So what's the effective action here? It's going to be an effective action in little d dimension. What action leads to that? Exactly the same, right? So what you did, okay, so now let's see what you did. So, notice that the honest way of deriving it is compute the equation of motion, restrict the equation of motion to a massless sector, and derive a new action. But now I'm showing you a quick and dirty way. A quick and dirty way is saying that, well, for the massless mode, you can assume that those guys depend only on x mu, right? And so then when you compactify it, so you have an integral over dxd, dx, and then I have a square root of minus gd, right? And then a square root of g dd, right? And then I have times minus 1/2 del mu phi. The reason being is that if my scalar depends only on x mu, so in this summation, I can replace the summation with respect to x mu. Now, in the approximation that we've been doing, this guy is 1, and I can compute the integral. So the integral simply gives me 2 pi r times the action. So what I'm telling you is that a quick and dirty way of getting an effective action starts with a higher dimensional effective action and assumes that all the fields does not depend on xd. So, however, you immediately know what are the limitations. So let me write it down. To get action in little d, which is capital D minus 1 dimension, start with d-dimensional action and compute it assuming nothing depends on xd. Okay? So that was a quick and dirty way. And so here we see the limitations of this procedure. So the limitations of this procedure is that in this way you get only the action for the massless mode. Okay? So this truncates to massless mode. Okay? But at the end of the day, that's what we are after, right? So we are after the effective action that describes light degrees of freedom. And so we can do it. So that immediately tells us how we can achieve this. Derive it. So we start with the action, which is Einstein-Hilbert term. Okay. And so first, what I have to do, I can parameterize for convenience. I'm going to write it down, GDD component of the metric as e to the 2 sigma. Of course, all the fields that you see now depends only on x mu. Now here I have a Ricci scalar. So first of all, this minus gd, I'm going to go to minus g little d times e to the sigma. Okay. And then I need to know how does my Ricci scalar will look like once I parameterize metric in this form. Right? So I just have to evaluate my d-dimensional Ricci scalar when the metric takes this form. And you can open a Wald book, and you will find out that this Ricci scalar in d dimensions takes the following form. So it's a Ricci scalar in little d dimensions. And then you have a contribution from the scalar field, e to the minus sigma, now plus q of sigma, and there is minus a quarter into the 2 sigma f mu. So again, here there is no mystery. What you do, you just evaluate a Ricci scalar in higher dimensions, and you will get a Ricci scalar in the lower dimension plus some kinetic term, or e to the sigma, plus some kinetic term for the scalar sigma, and then there is a Maxwell Lagrangian, right? So this f mu, is del mu a mu, and this del mu of f mu. Okay? So now all you have to do is just plug it in, and you will get an effective action. I'm not going to do that. Well, I'm gonna write it down the answer. So it's 1 over x times 2 pi r, an integral over little dx. Okay, so here the integral was over manifold in d dimensions. This is an integral over a manifold in little d dimension. And here I have a square root minus gd, e to the sigma. And what do I have? I have little rt, and then I have minus 1/4 e to the 2 sigma, e to the 2 sigma, f mu. Okay? So any questions? Why are you guys not asking questions? Right. So what happens? Why am I not writing this thing? Okay, so let's see what happens.
Oh, that's the inversion.
Exactly. So that's a total derivative that we can drop out. So this guy is a total derivative. And so I dropped it out. So there is the scalar sigma mu doesn't have a contribution from here. It will still have a kinetic term. You guys know how it will get a kinetic term? It is a dynamical degree of freedom. So it must have a kinetic term. Where does it get a kinetic term if you look at this action? No boundaries. We got rid of the, by saying that that's a total derivative. One way to do it is to say that there is no boundary. So I'm going to assume there are no boundaries. Where does this guy get a kinetic term? Before we ask this question, what is, just for you to be sure that this guy must have a kinetic term, what's the physical meaning of this scalar statement? Guys, what is the physical meaning of the scalar sigma? Where does sigma come from? The sigma comes from this. Right? So what's, if I ask you, what is the length of a circle? What are you going to do? So the length of a d-dimensional circle, you're going to evaluate the integral of dxd. Right? What are you going to do? You're going to put square root of gd. Right? So that's an invariant length of the d-dimensional circle. So e to the sigma times r. So e to the sigma is a scalar that changes with the radius of a circle. That's your modulus. Remember that when we talked about compactification, when we talked about string theory on networks, we said that there will be moduli. And so here you explicitly see that there is a scalar field shows up which controls the size, the invariant size of the scale of the circle. Sigma is a modulus that determines the size of the P circle. Now, once we understand that that's a size of a circle, it must be a physical field. It must have a kinetic term. If something doesn't have a kinetic term in the action, it is a constraint. It cannot lead to any dynamics. So my question to you, where does the kinetic term come from? You told me you know the law. All right? You know? What will happen? This is analog of the string frame. If you go to Einstein frame, you have to absorb this by redefining. Doing so, you will generate a kinetic. Thanks, great, perfect. Okay, I'm happy. You guys are learning something. Okay, let's continue. Right? So what we did this simple example. So we looked only at Einstein-Hilbert term, but now let's go ahead and look at something that we derived before. So we're going to look at the effective action for the string. So I'm just going to write down. It has two pieces. I'm going to write down the first piece and then the second one. So the first piece is going to be this. dxd square root minus gd r plus 4 nabla m5 right? So the only thing that happened here is that we have, well, when we talk about bosonic string, d equal 26, and then 5 is a dilaton, right? And so for now I am missing B mu nu field. Remember that there was B mu nu field, but actually I have to say not B mu nu, but rather B BMN field. And so for now we are missing it. We'll go back to it a bit later. So this guy, that's why I put the subscript 1 to denote that this is not complete. So now what will happen after I do Kaluza-Klein reduction? Actually, there was something that I missed here. So it's e to the minus 2,5, right? So it's a string frame metric. And so now I'm just going to do a Kaluza-Klein reduction on a circle. So what will happen is that I will have pi r over kd squared, right? Actually, that's exactly the term that we see here. And then I have an integral dxd, and then I have minus gd to the 1/2. So now my dilaton will get an additional contribution, right, coming from that sigma. So it will be minus 2,5 plus sigma. Okay, and then what I have little rd minus 4 nabla 5 nabla sigma plus 4 nabla 5 nabla 5, and then minus a quarter e to the 2 sigma f mu f mu. Okay, so the only thing different from what we discussed before is this term. Okay, so where does this term come from? Well, so what you pointed out before is that this is a total derivative, but in order to see that it's a total derivative, you have to integrate by parts, right? But now, see here, you multiply not by e to the sigma, but you multiply e to the sigma, and then there is a contribution from the dilaton, and so that's exactly where this piece will come from once you integrate by part. There will be no term nabla sigma squared. Okay, but there will be this contribution. The rest is unchanged. Okay, so very good. So actually, what I can do, I can change it. A little bit further. So I can write this action in the following form: AD squared integral e to the minus 2 phi. I put a subscript e here, and then I have RE minus nabla sigma squared plus 4 nabla phi d squared minus a quarter e to the 2 sigma f mu. Okay, so what I did here, I just introduced a little d-dimensional dilaton by simply defining it to be phi minus sigma 2. And so you can see that if you do this gymnastics, then this nabla phi nabla sigma term will produce you this kinetic term for the sigma. Okay, and so again, now if you go back to Einstein frame, so this is a string frame in little d dimensions. So if you go back to the Einstein frame, so then what will happen is that you will get the right sign for the kinetic term for the dilaton. So sign for nabla phi d squared is correct in Einstein frame. Okay, notice, okay, so is there anything else? No. Okay, great. So any questions so far? Again, we did something very, very straightforward. We took part of the gravitational action for the bosonic string. We reduced it on a circle, and what we did get, we got a U1 gauge theory, right? We get gravity and little d dimensions, and then we get the dilaton, and we had the dilaton before, but we also got one additional scalar. So now what I want to do, I want to comment on massive fields. Okay. So remember, so our effective action includes only massless fields. And what we showed earlier today, that those massless fields are necessarily in this simple toroidal compactifications neutral. So they are neutral under U1 symmetry. Okay. So the massive fields, they have charge, and so massive field are charged. So in particular, what will happen if they are charged, their kinetic term will not be defined by nabla mu, right? But what we will have to go, and it will come up naturally if you study massive fields. So this nabla mu will turn into a covariant derivative. So what you will have, it will go into a d mu, which is equal to nabla mu plus I pd times mu. And so remember that in the case that we looked at, it was IN over R a mu. Now normally we want to define charges to be integer, right? So here the Kaluza-Klein charge was the same as this Kaluza-Klein momentum, but we want to define charges to be an integer. And so in that case, what we can do, we can write this down as IN R mu tilde, where I mu tilde is simply 1 over R a mu, right? So I can redefine what do I mean by my gauge potential. And so once I redefine this, then all the Kaluza-Klein charges will come up to be integers. Okay. So now once I make this redefinition, in the effective action, the f squared term will change. Right? So if you do this redefinition, then f mu nu will go into R times f mu nu tilde, right? And so in the effective action here, what I can do is I can put tildes here and put R squared above. And so with this normalization, all my Kaluza-Klein charges will come up to be integers. Okay? All right, guys. So now I want to talk about something very exciting. So in general, we have how many couplings we have in this here? Look at this effective action and tell me how many coupling constants we have.
Just one.
One is Hertzians. Why do we have two, right? So one coupling is the gravitational coupling here,
Two, yeah.
and the other coupling is the gauge coupling, the coupling in front of the Maxwell field. Now notice that in the case of, if you write down arbitrary theory, right, there is no reason on the world why those guys have to be related. You can see now that when you do a Kaluza-Klein reduction, when your gauge field is not an arbitrary gauge field, but the gauge fields that come from a higher dimensional metric component, then that puts a constraint on what is the gauge coupling. Okay, and so let's discuss this in more details. So what we talked about relation between gravitational and gauge couplings. So upon KK reduction. Okay, so this is kind of, if you wish, goes back to the idea of how we can unify forces, how we can unify particle theory with gravity. Because if everything comes out from the string theory, there is a relation between couplings. And so the simplest example how that would show up is evident already in this Kaluza-Klein reduction. So a gravitational coupling in d dimensions, 1 over little d squared, is equal to pi r, gravitational pi r times gravitational coupling in 1 dimension higher. Now, what is the gauge coupling, right? So the gauge coupling is defined by d-dimensional gauge coupling. I have to look at the coefficient, minus 1 over 4 gravitational gd squared, the one that is in front of properly normalized Maxwell charge. By saying properly normalized, I mean the one that leads to integer electric charge quantization. In this case, Kaluza-Klein charge quantization. So in our case, you can see that 1/4 gauge coupling squared equals to what? Equals to pi r over kd squared. And then I have a 4, 1/4. And then I have r squared times e to the 2 sigma, but that's just an invariant length squared of a circle, right? So remember that, so this invariant length of a circle is e to the sigma times r. Or better to say invariant radius of a circle. Okay? And so now you can see that this is exactly the same as a gravitational coupling. And so from here, you get the relation that the gravitational coupling is related to gauge coupling in this way. Okay, so the original idea of Kaluza-Klein, when Kaluza-Klein tried to think about U1 electromagnetism as coming from five-dimensional gravity, you already have a prediction on the strengths of a U1 coupling, right? Given the size of a circle, and then you actually run it out, and you find out inconsistency.
I did not think how we get L squared, so it's R. We have R squared.
Well, right, so I have R squared times e to the 2 sigma. But e to the 2 sigma is, again, R is coordinate length, and L is the invariant length, which includes also the metric component. Okay, guys, so any questions so far? No. So what we discussed only one part of the bosonic gravity, right? This is S1, but there is additional gravitational action, and so we'll go back to your question, indirectly related to the question we've been asking before. So there is a second term in the actions that involves dv nu field, right? So now we look at this, the remaining massless field that we have in our bosonic stream. And so it come up with the effective action in d dimensions. And I have minus gg square root e to the minus 2 pi, and then I have h and p, where h is the field strength corresponding to dU. So h equals dE as a whole. Okay, so now we have to do exactly the same exercise, and we have to do a Kaluza-Klein reduction of this term. So let's see what will happen. So those guys, that's a completely. Let's think in terms of their VMN, right? Because h is h can be evaluated from V. So there are two ways. So that's an antisymmetric tensor, and so once we decompose it into mu and d index, there will be a component of this type, right? dv nu. So this is just antisymmetric field. In little d dimensions, right? But then there is another component, and the other component is when one of the indices is mu, and the other index is d. So now it is obvious if you think what are the transformation properties under the remaining diffeomorphisms, and this guy transforms as a vector. So what you get an additional U1 gauge field in d dimensions. Okay, and I'm not going to go into details, but you can show that this is indeed, indeed a gauge field. the reason why it's a gauge field because B mu nu has its own gauge transformations, and so some part of them will become gauge transformations of this gauge field. So this action, I'm just going to write down the answer. What will happen? So you have minus pi r over 12 kb squared x squared minus gb e to the minus 2 pi d. So I'm going to call this guy b mu tilde, right? Lower dimensional antisymmetric field. So here I will have h mu nu rho tilde, h mu nu rho tilde. So it's exactly the same way we define the field strengths in little d dimensions as well. And then there is additional gauge field, plus 3 e to the minus 2 sigma f mu nu prime f mu nu prime. Okay, so so everything I was telling you before kind of looks similar as far as this additional gauge field is concerned, but something is very drastically different. And you will appreciate this difference in a little bit. So all we did now is a Kaluza-Klein reduction doing a field theory. We're still doing a field theory. There is nowhere in place the string theory is. The only place where the string theory comes in is by saying that, look, besides S1, there is this S2, and it says that there is a very specific action that you have to live with. But everything else is just a field theory discussion. I never used ideas from string theory so far. So what we are concluding that once we do a Kaluza-Klein reduction, in little d dimensions we have U1 cross U1 symmetry, so there are two gauge fields. And so this guy has charged state, right? Has charged state. However, this guy, you can do a careful analysis by writing down the equation of motion, and rather than doing a quick and dirty one, by simply evaluating the action, assuming that nothing depends on the compact coordinate. You can do a careful analysis, and you will find out that this gauge field does not have any charge states. Okay? So, no charged massive states. So that sounds like, the question, okay, so what? Not a big deal, right? In a quantum field theory, that would be the case. But what we're going to discover a little bit later today, that actually string theory will provide charged massive states under this U1 prime. And in fact, it will make those two U1s being completely on the same footing. And then what we're going to do, we're going to discover a symmetry in the string theory. And the symmetry in the string theory, what it will do, it will simply flip these two U1s. Okay? But what I want to emphasize right now is that in a field theory, there is a huge asymmetry. So everything that we're going to talk now from is going to be very specific very specific to string theory and has no counterpart in field theory. And in fact, well, you will see in a second that there will be more to it. So we will discover non-abelian gauge symmetries as well. Okay, so any questions so far? I'm done with quantum field theory, and we now move to string theory. All right. Okay, so our string theory, as you know by now, is just a conformal field theory on a world shape. So what we're going to do now, we're going to study compactification in a CFT. So toroidal, Gaussian rectification. Okay, so I'm just going to again look only at a single scalar. All the remaining scalars are the same. So I'm going to assume that my scalar x is periodically identified with the period 2 pi r. In fact, this is some of your homework assignment in part 1 was to actually understand. So everything that I'm going to talk about, I'm not going to derive this, solve the problem for you, but I'm going to use the answers that you've seen before. So also I'm going to assume the GDD equals to 1. And so now the effective, so the worldsheet action here, I have 2 pi alpha prime over the worldsheet, d2z, del x, del bar x. Right? I'm just looking at, there are additional scalars and I need exactly 25 of them to cancel conformal anomaly. But I'm not going to do anything with them. They're going to go along the right. And because the theory on a worldsheet is a free theory, one scalar doesn't talk to another one, I can just look at the scalars which are non-trivial ones. Okay, so the only thing I did, I just said that my scalar is periodic. And I wrote you the Polakov action. It has exactly the same form. The Polakov action doesn't care is the scalar periodic or not, right? The reason is because it involves only local objects. It involves del x. And so what you're going to do, you're going to get same equations of motion, same operator product expansions, same contribution to worldsheet stress energy tensor. Everything is going to be exactly the same because all these properties are determined by the local properties. And I didn't change the local properties that x is a free scalar. All I said that it's periodically identified. However, so periodicity of the scalar, nonetheless, when we do quantization, has two effects. So one effect, so periodicity, is two effects. And so those effects are, well, first of all, again, my wave function has to be single valid as I go around the circle. What that means, and if I go around the circle, so my wave function will pick up a phase 2 pi r times I times p, where p is momentum around the circle. And so the fact that wave function must be single valid tells me that I have this quantization condition. So I derive exactly the same quantization condition as I have in quantum field theory, right? As in Q at T. Okay. So the momentum along the compact direction must be quantized. But then there is additional property that is very specific to string theory. So that property tells you that, well, before we looked at closed strings, and so closed strings only impose this boundary condition, right? So, so the field X on a worldsheet of a string must be single valid as we move along the spatial sigma coordinate by 2 pi. It must go back to itself. However, the point now is that the field X is itself periodically identified up to 2 pi r. So now I can relax this condition. And when I consider closed strings, I can simply require that once I go along the worldsheet coordinate sigma, it winds around along the compact direction integer number of times. So I'm just going to say that it's 2 pi r times omega, where omega is a winding number. It is a winding number. So now I still have the physical condition that in the physical space, what is happening is that my fields are single valued at the same physical position, right? Because as I go integer number of times, I'm back at the same point in the physical target space. Okay, so what I can do, I can require that my string 1. Okay? So that's very special if you think that's actually the origin of all the beautiful things that the string theory will tell us now. It comes from here. And you understand why it is very different from quantum field theory. Quantum field theory is a local theory. It describes local excitations. And here what we have some very non-local effect. The string winds around the compact direction. Okay? So you can ask me, why do I have to care about that? Why can't I simply say, I don't care about winding, and I'm just going to look about the states which don't have any winding, right? So I'm just going to quantize my strings in such a way that omega is equal to 0. Well, the problem is that you can't. Okay? You will get an inconsistent theory, and I'm going to try to explain you why that is the case. So, suppose I look at a simple tree-level diagram, right? So I have a closed string that propagates. So if my string winds omega number of times here, and it propagates freely in the space-time, I cannot change the winding number. Okay? So a winding number is a topological property. It cannot change under any smooth evolution. So a winding number at tau equals minus infinity is going to be the same as a winding number at tau equals plus infinity. So omega is conserved. Omega is a topological conserved quantity. However, it doesn't mean that the winding number doesn't change on the interactions. So what could happen? What could happen is that I have a diagram in which my string splits into two strings. So now, again, any process that occurs in the string theory must have conserved winding number. But it is the total winding numbers that must be conserved. So for example, here, I can start with a string that has no winding number, as omega equals to 0. But after the interaction, as long as there is a possibility for string to wind, I can end up with a state that has a winding number plus 1, and the other string that has a winding number minus 1. Whether you have plus 1 or minus 1 relates to in which direction you wind. Okay? So this is an example of an interaction. It has a non-zero probability, and this is an interaction which leads, you start with a string no winding, and you end up with a string that have winding number. What this tells you is that if you are by hand say, I'm not going to look at the winding number, you will get an inconsistent series. In fact, you will get a series that will violate unitarity. Because this process has a non-vanishing probability, and so if you remove this process from your Hilbert space, if you remove those states from your Hilbert space, you cannot conserve probabilities. So you have violated unitarity. So winding numbers are necessary, and in fact, any winding number must be included. Okay. So now I'm just going to go ahead and we're just going to do exactly what we did before. So del X is just a holomorphic path, so those are left movers. I can expand them in terms of oscillators, and I will get exactly the same expression as I had before. So here, 1/2 is minus infinity to plus infinity. So here I have alpha m, that n plus 1, and for the anti-holomorphic plot, for the right movers, I have minus I of 1/2 plus infinity. Alpha and tilde delta plus 1. So again, the reason why the expressions are the same as before, because you can see that those things are determined by the local properties, right, of our scalar. And by making, by compactifying the scalar, we have done nothing. Okay, so all these things are the same. So now remember that we defined a Will-Sheet momentum, right? So this is a Will-Sheet momentum. So the way how we define a Will-Sheet momentum, so we constructed a conserved current associated with some Will-Sheet translations. And so the momentum takes this form. It's an integral dz del x minus dz bar del bar x. Okay? And so we can compute what is the Will-Sheet momentum in this case. And so it takes exactly the same form as before. Alpha 0 plus alpha naught. Okay? So the next thing, so I'm just repeating the same steps how we did before. How do we relate alpha zeros in this oscillator expansion of S field? Now, remember that in order to get, that was not enough, right, for us to determine alpha 0 and alpha naught tilde. So what we needed to use, we need to use a periodicity. So before, what we said that a field X must be single valued, and so in particular, X at 2 pi minus X of 0 was equal to 0 in our case. But now I convinced you that we have to allow non-trivial winding. So in our case, X of 2 pi minus X of 0 can be an integer number times the length of a circle. So what this corresponds to, I can evaluate this once I know the mode expansion on my field. And so this is just an integral of dz del x plus dz bar del bar of x. Right? Just in a normal way, how you would evaluate the length of a circle, you take a derivative and you integrate over the coordinates that parameterize the circle. Okay. So you can substitute the mode expansion and evaluate that integral. Right? Again, it's just simple residue theorem that will give you the answer. And so what you will find out that the answer is going to be equal to 2 pi alpha prime over 2, 1/2, and then I have alpha naught minus alpha naught equivalent. Again, it just depends on this alpha naught and alpha naught equivalent. Now you have two conditions, right? So one condition is that the difference between 0 oscillators equals to 2 pi r times omega. And the second condition, the sum of two oscillators equals to momentum. But we understand that this momentum must be quantized, so it's equal n over r. So I have two conditions and two equations. I have two equations on two unknowns, the zero mode oscillator, so I can solve them. So what I will find out that P left, the left moving momentum, that I'm going to define it the same way how we did before. 1/2 alpha naught, just proportional to the alpha naught oscillator, will be equal to n over r, right, plus omega r over alpha prime. And the right moving momentum, so P right, is going to be equal to 2 over alpha, 1/2 alpha naught tilde, so it's going to be equal to n minus r minus omega r over alpha prime. Okay. So the difference now, once we allow a compact direction, there is a difference between left moving and the right moving momenta, and that's sensitive exactly how our string wants. And those of you who did the appropriate problem in the homework assignment, you should have seen this already. All right, guys, so let's make a 10-minute break, and after the break, we will continue. We will look at the spectrum of the string, and we will see how T-duality and non-abelian gauge symmetries appear in string classification.